talking about surveillance and surveillance radars without hesitation, repetition, or deviation starting now. Surveillance in aviation plays a crucial role in ensuring the safe separation of aircraft from one another, providing controllers with an accurate and reliable picture of each aircraft's position in the airspace. This is primarily achieved through surveillance radar systems, although other types of surveillance equipment such as ADSB or automatic dependent surveillance broadcast are becoming increasingly common. Before the advent of radar, air traffic controllers used procedural control methods to separate aircraft by using data related to distance, time, and altitude, often communicated via radio reports. However, procedural separation required greater spacing between aircraft, reducing the overall efficiency of air traffic management. The introduction of surveillance radar allowed for a much more efficient and safe management of air traffic. Surveillance radar can be categorized into two types: primary surveillance radar, PSR, and secondary surveillance radar, SSR. PSR works by sending out invisible electromagnetic waves in specific directions. When these waves hit an object, such as an aircraft, they bounce back to the radar system as an echo, indicating the presence of the object. The position of the aircraft is then determined based on the direction and time delay from the original transmission. However, PSR only informs controllers that something is in the airspace without providing details about what that object is. Controllers need to rely on additional sources such as radio communications or flight plans to identify the aircraft. Additionally, PSR can sometimes return signals known as clutter from non-aircraft sources such as birds, ground structures, or weather conditions like rain or snow. On the other hand, SSR provides much more detailed information. SSR works by utilizing an aircraft's onboard equipment called a transponder to send additional information back to air traffic controllers, including the aircraft's call sign, altitude, and potentially even ground speed. Some of the information transmitted is dependent upon the transponder mode, such as Mode A or Mode C. This information significantly enhances the situational awareness of controllers, reducing the mental workload needed to match flight information with radar dots on the screen. The stronger and more distinct signals from the SSR are also less affected by clutter compared to PSR. The SSR system typically assigns a unique 4-digit code, referred to as a squawk code, to each aircraft, which the pilot dials into their transponder. When the ground-based radar receives this code, it matches it with the flight plan data and displays the aircraft's identity on the controller's screen. In addition to primary surveillance and secondary surveillance radars, newer technologies like ADSB are beginning to replace traditional radar systems. ADSB references satellite navigation systems to determine an aircraft's position, automatically transmitting this information to air traffic control and other aircraft in the vicinity without any pilot or controller action. ADSB's capability to broadcast precise location data to anyone with receiving equipment marks a significant advancement in air traffic surveillance technology, promising to further improve both the safety and efficiency of the air traffic management system. Together, these surveillance systems form the backbone of modern air traffic surveillance and collision avoidance, allowing controllers to monitor aircraft with high accuracy and ensure that separation standards are maintained to prevent mid-air collisions. This complex interaction of technologies is essential for maintaining the safety and efficiency of the global aviation system. If you liked this video, don't forget to hit the like button, leave your thoughts in the comments, and subscribe for more aviation content.